Good morning, everyone. This morning, we're going to kind of do the same thing we did yesterday, but now with rational functions. So just like yesterday was kind of a whirlwind tour of polynomial functions, now we're going to have a whirlwind tour of rational functions. And to facilitate speeding this up a bit, I arranged for everyone to just get a copy of the note so you can kind of follow along, jot down things as you go. So I just want you to listen, okay? Which means everyone should be fairly quiet here so we can all listen together. Okay, and I'll talk through some of the things, and that will give you way more time to actually practice it. Okay, so after this video is done, you're going to get into groups like we usually do and have a couple questions and work through them together to get a handle on how this stuff works. Okay, but again, just want you to watch the video, follow along on the note, jot down things if you need to. And we'll go through it that way, and that should hopefully speed it up a bit because it was kind of long yesterday. So again, you'll have this in front of you, but to review, key things for rational functions. Okay, the main thing that comes up that didn't before are asymptotes. Okay, these can occur. There's kind of three varieties of asymptotes that can show up. Okay, there's the vertical ones, right, and these are created by the roots of the denominator. Okay, so when you factor the denominator, find your roots. That means you're dividing by 0, and typically that creates an asymptote. Once in a while it creates a whole, but most of the time it's an asymptote. Okay, there are also horizontal asymptotes. Okay, and to find these, we need to think about end behavior, right? What happens as we go towards positive infinity, and what happens as we go towards negative infinity. So you can use this, you can figure this out with test points, or you can play with infinity a little bit, and we'll hit that as we go through here. Okay, there's another type, right? There's oblique asymptotes. Okay, this occurs basically when there's a mismatch between the numerator and the denominator. The numerator is bigger. Okay, if the numerator is 1 degree larger, so say you have a cubic function over a quadratic function, then you will tend to a line that is not horizontal, right? You'll have a slant asymptote, and that's where your function heads towards. Okay, bigger differences in degrees produce other behaviors, but you probably would have seen oblique at least a little bit in advanced functions. Okay, so those are the three that you can potentially have to deal with. Okay, and of course, in terms of key features, basically everything we did yesterday, right? Knowing where your roots are, knowing where your y-intercept is, finding intervals of increase and decrease. Okay, all that stuff is still the same here. Okay, so again, there's just one example. We're going to go through the process with a rational function. You have it in front of you, and we'll just kind of hit some of the key things here. All right. So we're going to sketch the function f of x is equal to 1 over x squared plus 2x minus 3. So again, for the purpose of knowing what we're dealing with here, it'd be helpful to factor the denominator. Okay, so when I factor that, it turns into x plus 3 and x minus 1. Okay, so now we run through our process from yesterday. Okay, starting with the domain. Okay, well, the only problem with the domain is these asymptotes, right? I have a root here, which is at -3, and a root at 1. Okay, I can't cancel with the numerator, so those are going to be vertical asymptotes. So one way of writing this is sort of the grade 11 way, right? X cannot equal -3 or 1, and x is a real number. Okay, using the interval notation, everything else is fine. So I'm okay from negative infinity up to but not including -3, union with -3 to 1, union with 1 to infinity. Okay, so that is my domain. I just have some issues at those 2 points. Okay, intercepts. Okay, well, starting with the x-intercept, I don't have any x's in the numerator. I can't make that equal to 0, so I don't have an x-intercept. Okay, for the y-intercept, we just plug in 0. Okay, when I do that, I'm going to end up getting -1/3. Right, these equal to 0, 1 over -3, and that's my y-intercept. Okay, next thing on our list is asymptotes. Okay, we've already mentioned this in the domain. Okay, but we know we have vertical asymptotes at -3 and 1. Okay, so now to look at, do we have horizontal, do we have oblique? Okay, so we're going to look at the end behavior here. Okay, and see what's going on. Now again, I'm not sure how you learn this in advanced functions. Probably depends on who taught you. Okay, so one way we can do this, okay, well, it's the limit as x goes to infinity. So we're going to plug in infinity and see what happens here. Okay, so just the numerator, some of the rules just to review. Okay, infinity times infinity is still infinity. Okay, infinity plus infinity, or really infinity plus anything, is still infinity. Okay, so down here I have infinity squared, so infinity times itself is infinity, plus 2 times infinity, which is infinity, minus, or plus -3, so that is going to be infinity. So I have 1 divided by infinity when I plug that all in. So as I go to positive infinity, I tend towards 0. Okay, and similarly from the other side, okay, I can show that as I go to negative infinity, it's also 0. So because my end behaviors are tending towards 0, that means that I have a horizontal asymptote at y equals 0. So the x-axis is my horizontal asymptote. Okay, next thing on the list is symmetry. Okay, again, won't go too far into this, but if you do your test and plug in negative x and see what happens, okay, you will find it does not have even or odd symmetry. So it's not balanced around the origin or the y-axis. Okay, so that's the first 4 things. So now we're into increase and decrease and max and min. So this is where we need to take the first derivative. Okay, so again, this is where all those rules we've learned are really going to come into play, especially here, because now we have rational, and it's going to get more complicated. Okay. So because my numerator was 1, okay, it's going to be a little easier just to do this flip, right? I had 1 over x squared minus 2x x squared plus 2x minus 3. So I'll just rewrite that as all that to the -1 so I can use the chain rule. So let's start taking our derivative. And actually, I think I jumped a step here. So let's do it on the side. Right? If I start taking a derivative, right, the -1 would come down. Okay, and the inside stays the same. Okay, and the outside is -2. Then I take the derivative of the inside. Okay, so I multiply that by 2x plus 2. Okay, so right, that's using the chain rule to start my derivative. Okay, when I bring that back together, the -2 will push my quadratic back into the denominator, and -1 times 2x plus 2 is -2x minus 2. Okay, and because I'm interested in critical points, I get zeros from roots of the numerator. So I'm going to factor this a little bit. I have -2 times x plus 1. Okay, so again, I would get a critical point from here. Okay, because it makes my function equal 0. So x equals -1. Okay, the asymptotes are going to be important as well. Okay, and so I factored this as well. The original factors were x plus 3 and x minus 1, so I'll just have each of those factors squared. Now, Okay, so these three things are going to be important. That's where I can possibly switch from increasing to decreasing, and so on. Okay, so you'll have this in front of you, but we do an interval chart. Okay, note the -2 is really important there, so I put it as its own factor. Okay, and here's all the other pieces. Okay, so my derivative overall is positive for the first two intervals, negative for the next two. Okay, which means it is increasing in the first two intervals and decreasing in the next two. Okay, and specifically here, at my critical point, -1, okay, it's flipping from increasing to decreasing. So I must have some kind of a local max there. Okay, and that's essentially what the first derivative test is. I look at this chart, it switches from increase to decrease, so it must be a maximum, right? It was going up, it's coming down, I have a local max. Okay, specifically, where is that maximum? Well, if I take -1 and plug it back into my original function, I will get -1 and -1/4 as my local max. Now, the other ones, okay, it's increase, increase, decrease, decrease, so these definitely aren't max or mins. Okay, but remember those were asymptotes, right? 1 is an asymptote and -3 is an asymptote. So that's what's happening at my other two breakpoints. Okay, so we've got that. Now we move on to the second derivative. Okay, so to check for inflection and concavity, we're going to go to the second derivative. Okay, so again for reference, here's the first derivative. So to run this, now it's not, we could bring this up and make it product and chain. Okay, it's already a quotient, so we'll just go ahead and use the quotient rule. So the derivative of the top is -2 times the bottom. Leave the top and multiply it by the derivative of the bottom. So that's chain rule. Okay, right, bring down the 2. Got my x squared minus 2x minus 3. Do the derivative of the inside again. That's 2x plus 2. And now that's all over x squared plus 2x minus 3 to the power 4. Okay, my next step would be look for a common factor to remove. Okay, so I have my quadratic here squared. And over here, I have a single power of that. And in the denominator, I have that to the power of 4. Okay, so realistically, I've got my three kind of pieces here. I can divide this out once from each term. So that's going to reduce to exponent 1. This is going to be gone, exponent 0. And this one is going to reduce to 3. Okay, so that helps me tidy up my denominator a little bit. Okay, so I've reduced those down. Okay, and now it's a matter of just expanding and simplifying. Okay, so again, won't go through into too much detail here. Right, be careful with this negative. Right, I'm subtracting this entire expression, which is why when I expanded it out, I left it in the brackets for a moment to remind myself I have to subtract all those things. So when I tidy that up, I get 6x squared plus 12x plus 14 all over my quadratic to the power of 3. Okay, so now I'm ready to analyze. Okay, so first for the numerator, if you play with it a bit, okay, it doesn't factor, and even if you throw it into quadratic formula, it doesn't actually give you any roots. Okay, so I don't have any roots in the numerator, which means I don't have any inflection points. Okay, there's no inflection point. However, I do need to think about the asymptotes, because maybe the inflection switches as I pass from one side of the asymptote to the other. Okay, so again, we do an interval chart. Okay, the term on the top doesn't factor, and no matter what you pop in there, you get a positive result. Okay. We have our factors from the bottom. Okay, so overall, right, my second derivative is going to be positive here, which means it's concave up. It's negative in the middle, concave down, and here it is up. Okay, so again, now we have all the pieces we need to make the graph. Okay, so let's review what we had here. We had asymptotes at, I believe, 1 and negative 3. So here's an asymptote at 1. Okay, here's an asymptote at negative 3. Let's double check. Okay, we had no x-intercepts. Okay, we had a y-intercept at negative 1/3, which would be about here. Okay, we had a local max at negative 1 and negative 1/4, so just a little bit above my y-intercept there. Okay. We know that the shape is concave down in the middle, right, and it goes from increase to decrease. So I must have an upside down parabola in here. Okay, and I apologize, this is going to be really sloppy because I am drawing with a mouse. Okay, so something like that. Okay, in the other sections, okay, all I have to go on is that it approaches 0. Okay, one side is increasing, okay, and one side is decreasing. So if this stretch is always increasing, but there were no roots, the only way that could happen is if it looks like this. Okay, right? If I was approaching here from underneath, it would have to cross somewhere to be increasing, and similarly for decreasing. Okay, so that's what my graph is going to look like. So what I want you to do right now, okay, is we're going to do the normal procedure. Cards are going to be dealt, and you're going to go to the whiteboards so you can work on this. Okay, I'm putting the homework up here, okay, but I just want to highlight, okay, right here. So number 3, and it doesn't have to be ACE, okay, in your group, okay, and maybe if the class wants to collectively try A first, doesn't really matter, okay, but I want you to pick 2 questions from number 3. Okay, and if you only get through 1, that's okay, but aim to try to get 2 done as a group in the time you have left. Okay, so that's what I want you to do. Okay, again, for the weekend, okay, between the stuff from yesterday and today, if you know you need more practice, okay, then a little bit here and there over the long weekend, you should try to get a little bit of practice done to make sure you can get it down. Okay, but for now, again, small groups, please work on that. Okay, so thanks for watching. Okay, enjoy your practice and work hard, and I'll see you on Monday.